Hello, welcome back. Today we're going to be talking about how to model sequences. In particular, we're going to be using neural networks to model sequences. And as part of that, we will introduce recurrent neural network models. These lectures will be in two parts, and we will start with part number one. We will begin by introducing the problem of modeling sequences and why we would need something like a neural network model. Then we'll talk about how to encode sequences into vector representations that we can then use for many purposes. For example, predict properties of the sequences, predict what comes next, and so on. And we'll introduce what's in the box, what is a recurrent neural network, and how it relates to simple feed-forward neural networks. Let's begin with a very simple example. Here you see the value of a currency, US dollars compared to euros, as a function of time. And our goal is to now predict what happens next. So predict the value at a time point that we don't yet know. We've already seen how to solve these kind of tasks with feed-forward neural networks or linear predictors. We will first start by compiling a feature vector corresponding to the task that we are trying to solve. So for example, at time t, when we are trying to predict what the next currency value is, we can compile a feature vector that consists of previous values. So yt minus 1, yt minus 2, and so on. Here only 4 coordinates yt minus 4. So we construct a feature vector based on the previous values of this time course signal, and we call that feature vector phi of t. And we can now use that vector to try to predict what the outcome is, or the value at the next time point. Now, since we have the time course signal over a longer historical period, we can now use previous instances of constructing the feature vector here and knowing what happens next as training examples, and essentially slide through the time course signal to gather training instances of compiled history in terms of these 4 values for previous values, and then trying to predict what happens next. Let's now see how this can be done also with discrete sequences such as sentences. We have a sentence here: this course has been a tremendous, and we don't know what the next word is, and we are trying to predict what that word is. Our goal now is the same. We translate somehow the history of what we have seen into a feature vector, and then try to use that feature vector to make a prediction of what happens next. So for example, we can here just look back 2 words and translate each of the previous words into vector and concatenate the 2 vectors into an actual feature vector that we use for prediction. So we can take the word tremendous, that's the previous word, use a 1-hot encoding of that word, turn that into a very sparse vector with only 1, 1, and the rest of the words 0. And similarly for the word 2 steps behind, we turn that into a 1-hot vector and then concatenate the 2, and we get a long, sparse feature vector phi of t that we can now use to relate that to the possible outcomes, which are the words that come next. And as before, we can go back in the sequence, this sentence and other sentences that we have already seen, and then construct a feature vector based on the 2-word history. And now we know what happens next, and we can use those pairings of feature vector and the correct outcome as training instances. So why would we not solve the problem in this way? Turn a fixed length history into a feature vector and try to relate that to the outcomes of what happens next. The problem here is that we don't exactly know the length of the history that we should pay attention to. The more history we include, the longer the feature vectors will be, and the more complex the learning and prediction tasks will be. The other problem is that sometimes the history that we should pay attention to is variable length. There may be words at the beginning of the sentence that are quite relevant for predicting what happens towards the end, and we would have to somehow retain that information in the feature representation that we are using for predicting what happens next. So instead, what we need is a more flexible way of turning sequences into feature vectors. So let's look at a few instances of the prediction tasks where this type of flexible way of encoding sequences is quite relevant. One we have already seen, predicting the next word in the sentence, what happens next. We have here already a part of the sentence. We need to turn that into a feature vector such that we can use standard prediction tools to then predict what would happen next. Similarly, we can take the whole sequence, turn that into a vector, take the whole sequence or sentence here, turn that into a vector, and then predict properties that pertain to the whole sequence. For example, the sentiment of the sentence. In a more complicated prediction task, we can take that sentence, turn that into a vector, and try to unravel that vector, the same sentence written in another language. This is a structured prediction task that we will talk about later on. Now, the vector representations that we need in each of these cases are different. What we need to predict the next word should be summarized by this vector. What the whole sentence is for the purposes of predicting sentiment should be summarized in this vector, and the whole semantic content of the sentence should be captured by this vector. So when we learn these representations, vector representations, how to encode a sequence into a vector, we parameterize the process of turning this into a vector and try to optimize those parameters so that these feature vectors in each of these tasks would be appropriate for the prediction task that we are trying to solve. Now, we will separate encoding, which is turning the observed sequence into a vector, and then decoding is turning that vector into a prediction that we want to make. And in the case that that prediction is itself a sequence, we also need a summarization in that part, and we will talk about language modeling later on. So we have two tasks to solve here computationally. Encoding, turning a sequence into a vector. This is what we're going to be talking about today here in this lecture. And decoding, turning a vector also into a sequence, as in machine translation. And we will talk about that in the next lecture. Let's briefly look at a preview of what we can do once we've solved these encoding problems. We can take words as vectors, use them to turn sentences into vectors. We can take images, turn them into vectors. We can take events and other things, videos and other things, and turn them also into vectors. Now, after this encoding, everything is in the same representation. Everything is turned into a vector. As a result, we can easily relate objects, such as images, with sentences. We can also unravel these vectors back into those objects. So we can take a sentence, turn that into an image, take an image, turn that into a sentence, and so on. By operating in the setting where everything is turned into a vector gives us a lot of flexibility of relating and using very disparate objects in multiple different ways. And this is really a power of these continuous vector embeddings of objects. Let's see now in a little bit more detail how we can turn a sequence into a vector using a parametric transformation. A transformation that we can then later adjust on the basis of what we wish to use the resulting vector for. We're going to be doing this by applying the same transformation in a sequence, trying to summarize or turn a sequence into a vector piecemeal, one word here at a time. To do that, we will need to take what we have already, which we call context or state here, add new information, which in our case will be a new word, apply a box that is the transformation that combines what we have so far, the summary that we have so far, and the new information given by the new word, and turns that into a new representation of a state or the summary. And we can adjust the parameters to change the behavior of this transformation. This type of transformation that has an evolving state is called a recurrent neural network. So let's see what could be inside this box. Here we represent the state, the summary so far, in terms of a vector st. So what we have previously is then st minus 1. New information is given by the word. The word has a vector representation. Let's call that xt. And what the box has to do now is to turn the previous state as a vector st minus 1, added new information in the vector xt, and turn that into a new summary that combines the two, which we call st. So as a transformation, let's say st here is an m-dimensional vector. Okay, so our transformation now takes the previous state, which is also an m-dimensional vector, applies a transformation that tells us how the state would evolve in the absence of any information, given by this parameter matrix WSS. It's m times m parameter matrix. We add to that the new information that the word here, represented by, say, d-dimensional vector, brings in to the state. That transformation from the word to the state is represented by the parameter matrix WSX, and it will be an m times d-dimensional matrix. What's inside the argument of this tanh function now is an m-dimensional vector. So we apply that tanh transformation element-wise to turn that into a new representation of a state. So this is a simple transformation that takes previous state, new information, has some parameters represented by these two matrices, and I'm omitting the offset parameters here. These two parameters together then define what the theta parameters are in this box, and they are adjustable. So this is just a mechanism of turning that old information plus new information into a new state vector. And we can adjust it. We can adjust the parameters theta so that this box, this transformation, behaves as we want it to. So let's now apply our little transformation box here to the sentence that we have, so as to see how this actually works, how we are going to turn a sentence into a vector. So we start with a null vector. So S0 here, the summary, having not seen anything, is just an all zero vector. We get a new word, it's x1 here, and we're going to apply the box now with this previous state, with this new word, to get a summary of what the model thinks the summary of just the word efforts is. So we're going to apply that box. Here we have x1 and s0 again. And as a result, what we get is a vector representation of s1. What we believe so far, the summary of just having seen the word efforts should be. So that summary is now a vector, S1, and the process can continue. We can apply the box again. As a result, we have x2 here, we have S1 that we had previously calculated, we have a new word and, we combine the previous state, the new information represented by the word vector x2, and what we get here is S2, a vector that is now supposed to summarize what the beginning of the sentence efforts and should be as a vector. Okay? And recall that this, applying this box, is always specific to the parameters that we have, and therefore the vector that we get would be different if we used a different set of parameters. Now we can continue this all the way till the end of the sentence and get then the sentence as a vector. Okay? So we now have a procedure that takes parameters theta and the definition of the box. We can apply it sequentially throughout the sentence and turn that sentence into a vector. Now that vector now has parameters. Effectively, it depends on theta as well as on the sequence. And we can adjust those parameters to make this representation of a sentence appropriate for the task that we're trying to solve. Let's see how our recurrent neural network approach differs from a standard feed-forward neural network. As we have applied this box sequentially for each word, in response to each word, we turn the sentence into a vector. It looks like, as it's laid out here, unfolded along the sequence, it looks like just a feed-forward neural network. And indeed, it has many similarities. However, there are also a few differences. First, we will feed in input to each of these layers. If you think of applying a box as a layer in feed-forward neural networks, then now input is received at each layer as well as from the layer before. Layer before provides the previous state. The new input is the word that we are adding. The second difference is that now the number of layers in our neural network changes based on the sequence. Sentences vary in length. As a result, as we unfold this transformation along the sentence, we are effectively creating a feed-forward neural network that has a varying number of layers. The third difference is that since we are applying the same box as a way of turning the previous summary and the new information into an updated summary, we are applying the same parameters at each of these layers. So we are not adding parameters that depend essentially on the layers of the neural network. Learning these recurrent neural network models is very similar to learning feed-forward neural networks. As we turn the sentence into a vector, we make a prediction. As a result, we get an error signal. We back propagate that error signal through this layer-wise transformation, just as we did in a feed-forward neural network. The fact that the parameters are shared here just means that we add the contribution of each of the suggested modifications for parameters at each of these positions where the transformation is applied. One concern that arises with the backpropagation is the same as applies to very deep feed-forward neural network architectures. And that is that the gradients can vanish or explode. The sequences can be quite long, and we apply this transformation repeatedly. As a result, the issue of vanishing and exploding gradients is quite real for recurrent neural networks. And in particular, different architectures of the what's inside the box are tailored precisely to counter this issue. So let's take a few more examples about what can actually be inside that box. What we've seen so far is a very simple recurrent neural network. The problem with this formulation is that as we apply this transformation, we essentially forget the information that we had. We override it completely to get the new information. It is often helpful to retain or learn to retain some control over what is written over and what is incorporated as new information. This control over what we write and retain in the summaries or the state is typically done via another network called a gating network. A gating network here has the same input, same form of input as the state transformation itself, turns that into a continuous value between 0 and 1 here, not between -1 and 1, but between 0 and 1. And the output is, again, a vector of the same dimension as the state. And now we incorporate this gating prediction of what we should write and retain into the state update itself. So we take the previous form of the new state update that we would have previously just used directly. Now we take a combination of what we have previously and the new one and balance between the two using the gating network. So for example, here, the 1 minus gt, if I take the extreme values here, that could be, say, a vector of dimension m that has coordinates here 0, 1, 0, and so on. As a result, gt here is a vector of 1 minus that would be 1, 0, 1, and so on. So when 1 minus gt is 0, that means that we don't retain any information of the previous state in this form. We don't store the previous information. We overwrite that coordinate precisely with the update as we had seen before. When that value is 1, we keep all the information that we had previously and completely ignore the new suggested coordinate value. Now, we don't know how to control this state update, what to retain, what part of the coordinate space to retain at any given point in response to new information that we are getting, but we can learn to control this. And it is helpful to add this level of control into the neural network architecture. This is called a simple gated neural network architecture. Here's a somewhat more complicated recurrent neural network known as an LSTM or long short-term memory network. It has now multiple gates. It has a forget gate, input gate, output gate that controls how to read information into the memory cell, how to forget information that we've had previously, and how to output information from the memory cell into a visible form. So in this box here, as we apply it in the same way as before, the previous state that we have is actually now in two parts. There's the memory cell value as ct-1 that we had before, as well as the visible portion of the state ht-1. And it is the combination of the two that is now the summary. We get new information xt, and we turn that into a new summary ct and ht. Now, when we are updating the memory cell, we take the suggested new signal, as in the basic RNN, we would have just overwritten the state with this new information. Now we have an input gate that controls to what degree which of these coordinates of this suggested signal should enter the memory cell. We also have a forget gate that controls from the previous memory cell which of the coordinates we should erase information from. So when the forget gate has value 0, for one coordinate, we will completely erase the information that that coordinate had in the previous memory cell. So the memory cell update is helpful to retain information over longer sequences. But we keep this memory cell hidden and instead only reveal the visible portion of the state. So we take a 10-8 transformation of that memory cell signal. Since the memory cell signal is additive, it can increase in value. We turn that into a value between -1 and 1 by applying the 10-8, and then control what portion of that signal should actually be made visible. And it is this HT then at the end of the whole sequence, applying this box along the sequence that we will use as the vector representation for the sequence. There are many other alternatives in terms of the more sophisticated recurrent neural network architectures. LSTM is one of them that is still frequently used. So, key things to remember: how to use recurrent neural networks to turn sequences into vectors, solving the problem known as encoding. These recurrent neural networks can be understood as feed-forward neural networks along any particular sequence. Since they are unfolded along the sequence, we can effectively understand them as feed-forward neural networks whose architecture does change from one sequence to another. They can be trained in the exact same way as feed-forward neural networks, backpropagating the signal from the vector representation or where the error signal is, backpropagating along the sequence and nudging the parameters in the helpful direction. The feed-forward architectures suffer from vanishing exploding gradient issues, so do recurrent neural networks. Specific architectures such as the LSTM recurrent neural network maintain a better control over the information that's retained, updated along the sequence, and are therefore easier to train to do what we want them to do.